Module 12, problem set 4. Here we are asked to draw a major contributor to the resonance hybrid for NO2, nitrogen dioxide. Let's begin by identifying how many valence electrons we have. We have 2 times 6 for 12, plus 5 to represent the group number for the nitrogen. We have 17. And immediately we may recognize something peculiar about this particular molecule in that we have an odd number of valence electrons. But let's continue to ratchet through our algorithm. We'll place the nitrogen in the middle. We'll attach the more electronegative oxygens. We'll give everything an octet that needs an octet. And in coming up with that particular arrangement, I've utilized too many valence electrons. I've used 20, I only had 17. We'll take a lone pair off the central element, lone pair off least electronegative the adjacent elements. I'll introduce a double bond. I'm now using 18 valence electrons. And I recognize everything I do as far as the normal sense by removing lone pairs of electrons from central atom, lone pair of electrons from adjacent atoms, is affecting the number utilized by 2. So doing that again is going to bring me down to 16. What must happen, therefore, for me to utilize just 17 valence electrons? Somebody's going to have a single electron, all right? Will not have a pair of electrons. And in deciding, well, who's going to get only a single electron, nitrogen being less electronegative than oxygen, would stand to reason the nitrogen will have that single electron, still going to constitute what we will later call an electron-dense region. But I've now used 17 valence electrons. I have a radical on that nitrogen, and in nature what we tend to see is that NO2 exists largely as a dimer, where a molecule is in close proximity to another molecule. I recognize this as an example of a molecule that would exhibit resonance. I could just as easily have placed that double bond here. In nature, again, this nitrogen to oxygen bond is the same as this nitrogen to oxygen bond. It is intermediate in length and strength between that of a true nitrogen to oxygen single and true nitrogen to oxygen double. If I were to go through and assign formal charges, we would get a 0 here, we would get a -1 there, and a +1 there. Right. This negative formal charge on the more electronegative oxygen represents this as the major contributor to the resonance hybrid for NO2. All right, let's do the next question. And in the next one, we are asked to come up with 3 major contributors to the resonance hybrid for ClO3, 1-. This is the chlorate anion. All right, so how many valence electrons do we have to work with here? We have the chlorine in group 7, each of these in group 6, so 18 plus 7 for 25, plus 1 more for 26 valence electrons. All right, we will place the chlorine as our central atom. We'll attach those oxygens. We'll give everything an octet that needs an octet. Here that was everything needed an octet. And in coming up with this particular arrangement, I have used 26 valence electrons. Okay, so from the standpoint of the octet rule, things seem happy. From the standpoint of number of valence electrons utilized, again, things seem happy. Let's check formal charges, though. We'll recognize each of these oxygens right now stands at a -1, a -1, a -1. And if we were to assess the formal charge on that chlorine, it is in group 7, so we had 7 minus 3 plus 2 for 5. It right now has a formal charge of +2. All right, all non-zero formal charges and a high formal charge on that chlorine would tend to indicate this would not be a major contributor to the resonance hybrid. Is there something we can do to reduce those formal charges? And I recognize, well, yes, if I were to take and move or shift one of those lone pairs of electrons down here, I've now reduced the formal charge on that oxygen, or actually increased it from -1 to 0. This has now gone from a formal charge of +2 to +1, which you probably recognize if I did that again. Let's take a lone pair and shift them here, making a double bond. I now have a formal charge on this oxygen. It is also 0. Formal charge on that chlorine is 0. Something was going to have a non-zero formal charge that I could impart the -1 charge to the molecular ion. Oxygen is more electronegative than chlorine, so it stands to reason it should get that -1 formal charge. I would now indicate that this is a molecular ion that carries a -1 charge. And I could go through and draw the other two major contributors to this resonance hybrid. We're simply adjusting which oxygen is singly bonded and which oxygens are doubly bonded. So I'll now make this my singly bonded oxygen. Each of those doubly bonded still have the lone pair on the chlorine. That would carry a -1. And for the final form, we'll have that singly bonded oxygen here. These are the three contributors, major contributors, to the resonance hybrid for the chlorate anion.